T2.12. A study of 12,000 able-bodied male students at the University of Illinois found that their times for the mile run were approximately normally distributed with a mean of 7.11 minutes and a standard deviation of 0.74 minutes. Okay. Part A, about how many students ran the mile in less than 6 minutes? Okay, so for each of these questions, we're probably going to want to draw a picture. Okay, so we'll start with our normal curve, and we're going to label it N for normal. The mean is 7.11, and the standard deviation is 0.74 minutes. Okay, and for now, all we'll do is we'll label the mean 7.11 minutes. Okay, so for part A, about how many students ran the mile in less than 6 minutes? Okay, so let me just go ahead and make a copy of this. Do it right there. Okay, so this is part A. Okay, so our boundary value is 6 minutes, and we're looking for the percent that ran less than 6 minutes. Okay, I know 6 minutes is going to be somewhere on the left half. It's less than the mean. And we're going to want to shade the left tail because it said less than. Okay. All right, so that's the first step, drawing a picture. Next, we're going to standardize. Okay, so what's the standardized value of 6 minutes? All right, so the z-score is going to be the value minus the mean over the standard deviation, which is 6 minus 7.11 divided by 0.74 is negative 1.5. Okay. All right, so now let's think about this not in terms of the original distribution, but in terms of a standardized distribution. Okay. A standardized distribution has mean 0, standard deviation 1. So now the center is 0, and then our boundary value is the z-score, negative 1.5. Okay. Right, from here what we need to do is we need to take a look at table A, which I'm going to pull up here. Table A. Okay. Right, and so we're looking for a z-score of negative 1.5, and if you want to put the hundredths digit, it would be a 0. Actually, I already have it pulled up here. So the proportion that corresponds to that z-score is 0.0668, or 6.68%. All right, so the area 0.0668 or 6.68%. Okay? So there were 4 things there in that solution. Okay? A picture of the original distribution, a z-score calculation, a picture of a standardized distribution, and then using table A to get the area. All right, so that was part A. Let's take a look at part B. Approximately how long did it take the slowest 10% of students to run the mile? Okay, so the slowest students are going to have the longest times, not the shortest times. Let's do our work over here. Okay, so the slowest are going to be over here somewhere. All right, so we want that to be 10%, which means the other side is going to be 90%. Okay, and we'd like to know what the boundary value is, so we don't know the boundary value. Okay, all right, so this is a situation where let's just redraw it as a standardized distribution first. Okay, so as a standardized distribution, right, this would be centered at 0, normal, mean 0, standard deviation 1, right? And then this would be a z-score. So now the problem boils down to what z-score has 90% to its left and 10% to its right. Okay. All right, so let's go to the table here. And our picture, right, has the small tail on the right, the big tail on the left. So it doesn't look like that. Instead, it looks more like this, right? Big tail on the left, little area on the right. Okay. So we're looking for the 90th percentile. Okay. All right, let's erase these old marks and look for the closest thing we can find to 90%, so 89.97. All right, so I know the last digit's going to be an 8, and the other digits are going to be 1.2. Okay. So now the z-score we've found is 1.28 approximately. All right, now that we know the z-score, we're going to set up an equation where we can solve for the missing value. Okay. Remember, a z-score is the value minus the mean divided by the standard deviation. Okay. And we know the value, so we'll plug that in. We know the mean, so we can plug that in, and we know the standard deviation, and we can substitute that in as well. All right, so 1.28 is equal to this mystery value minus 7.11 divided by 0.74. Okay, and now we're just going to use algebra to solve. We're going to multiply both sides by 0.74, and then we'll have to add 7.11 to both sides. Okay, I'll just do the calculations off screen. Okay, plus 7.11. Okay, so after all the work, I got x is equal to 8 point, I'm going to round this up to 8.06. Okay. All right, so the slowest 10% of students, or the students with the longest times, 10% longest times, all ran 8 minutes and 6 seconds or longer. Okay. All right, we didn't leave ourselves much space, but there is a part C. Suppose that these mile run times are converted from minutes to seconds. Okay. Estimate the percent of students who ran the mile in between 400 and 500 seconds. Okay, so this is a conversion question. So I guess we should probably convert the original mean and standard deviation into seconds. Okay, so let's use another color here too. So the mean, 7.11 minutes, so 7.11 times 60, right, 60 seconds in a minute, that'd be 426.6 seconds as the mean, and then the standard deviation, 0.74 times 60, right, 60 seconds in a minute, that'd be 44.4 seconds as the standard deviation. Okay. All right. Let's clear off some space here. I can just remove all of this now. All right. So let's go ahead and draw. Maximize this a little bit. Let's draw a distribution. Okay, so it has the same shape still. It's just in seconds instead of minutes. So this is normal with a mean of 426.6 seconds and a standard deviation of 44.4 seconds. And we'll just label the center here, 426.6. Okay. All right, estimate the percent of students who ran between 400 and 500. All right, so 400 is going to be somewhere to the left. 500 is going to be somewhere to the right. And we'd like to find the percent in between those two boundary values. All right, so it's the same step as the first question. We're going to standardize both boundary values, draw a standardized distribution, and then use table A. Okay. All right, so our first z-score is going to be 400 minus 426.6 divided by 44.4. Let's calculate that. I know it will be negative, since we're looking at a value below the mean. So I'm going to round this to negative 0.60. Okay. The other z-score, that's going to be 500 minus 426.6 divided by 44.4. And that's going to be positive 1.65. Okay. All right, let's go ahead and draw a standardized distribution. Okay, so this is normal with a mean of 0 and a standard deviation of 1. Okay. The left boundary value is negative 0.60, and the right boundary value is 1.65. Okay. All right. From here, we can go ahead and use Table A to get some areas. And remember, these areas are the same as proportions. Proportion. Okay. All right. Negative 0.60. Okay, so there's the first two digits and the last digit. So the first z-score has a proportion to its left of about 27%, 0.2743. Okay. The other z-score has 1.65, 1.65. Okay, so I'm getting 95.05. All right, so neither one of those is the final answer. Okay, basically what it's saying is the percent of data to the left of z-score 1.65 is 95.05, and the percent of values to the left of the other z-score is 2743. So to determine the area in between, we can just find the difference of those two values. Okay, so the final step is to do 95.05 minus 2743, which is a difference of about 67%, 67.62. Okay, or you can write it as a percentage, 67.62%.